In this lecture, we will learn about limits involving infinity. So when it's limit involving infinity, so we have limits either x value approaching to infinity or negative infinity, or the value of the limit of the function turns out to be infinity. So the notation limit x approaching a f of x is infinity. The functional values goes to infinity when x is approaching a. So let's understand this definition using the graph here. What's the value of the limit of the function when x is approaching 0 from the right? 0 from the right, you're going to read the graph like this, approaching 0 from the right. You read the functional values, they're going higher and higher. So the values become larger and larger and they go to infinity. Similarly, when x is approaching negative 0, or like when x is approaching 0 plus, 0 minus, you read the functional values carefully, it's going to negative infinity. You also see these values in the graph. When you choose all the plus signs, plus 1, plus 0.5 and so on, the values are approaching towards 0, but the functional values are blowing up. It becomes higher and higher. It goes up to infinity. But when you choose the negative values for x, you see the functional values are becoming smaller and smaller and they go all the way up to negative infinity when you read the graph in this direction. So these have been discussed here. Next is the definition of vertical asymptote. The line x equal to a is called vertical asymptote of the given function if at least one of these statements are true. When the limiting value of the function either goes to infinity from the left, from the right, or the function itself, or negative infinity from the left, from the right, or the functional value itself, you call that particular line as vertical asymptote. So in this example, we saw that the limiting values go to infinity and negative infinity exactly on this y-axis, and the name of this y-axis is also x equal to 0. Any point on this y-axis, the x is 0. So this will be the vertical asymptote for the graph y equal to 1 over x. In the next example, you have an empty space. I want you to write a graph of y equal to tangent x and draw the tangent x graph. First draw two vertical asymptotes at negative pi over 2 and pi over 2, and then draw the tangent x graph. So you're seeing two vertical asymptotes here, two vertical asymptotes, which is x equal to negative pi over 2 and x equal to pi over 2. The curve goes as close as possible towards the vertical asymptotes, but it will not touch the vertical asymptotes. Next, you want to sketch a graph of an example of the function f that satisfies all these conditions. So name these conditions as 1, 2, 3, all the way up to 5. So you have the limiting values discussed at x equal to 2. When x is approaching 2, you have the functional value which is going to negative infinity. So I'm going to draw a vertical asymptote at 2. This is the asymptote at x equal to 2. Then I'm going to mark the infinity, negative infinity on the x and the y axis. So in the second definition, you have x approaches infinity. As x approaches infinity, the functional values goes to infinity. So we can draw this curve here. you see that x is approaching infinity, the functional values is also going to infinity. So this is our definition 2. Definition 1, the functional values goes to negative infinity when x is approaching 2. So approaching 2 from the right, we already have it. So let's draw one more curve which is approaching 2 from the left. So approaching 2 from the left or right, you see that the functional value is going to negative infinity. Then definition 3, when x is approaching negative infinity, you have the functional value going to 0. X approaching negative infinity, so you draw a nice smooth curve which is as close as possible to negative infinity line and show that the functional value is 0. This is your definition 3. This is 1 plus 2 and this is explicitly 2 as well. Then in the fourth definition you have the limiting value going to infinity when x is approaching 0 plus. Towards 0, this is 0. So when x is approaching 0 plus, you see the curve is going to infinity. So this is 4 as well. And the definition 5, when x is approaching 0 minus, the functional value is negative infinity. So 0 minus is approaching 0 from the left and you see the curve is going down. So this is your definition 5. So you have a nice neat curve which satisfies all these definitions, 5 definitions. Then you have the line y equal to L is the horizontal asymptote of the curve y equal to f of x. If these definitions are satisfied, x is approaching infinity, the functional value is L, or when x is approaching negative infinity, the functional value is still L. So you have a graph here. When x is approaching infinity, you want to read the functional value. Say this is 1 on the grid. You see the graph is approaching 1. Similarly, when x is approaching negative infinity towards the left in this direction, the functional value is still 1. So you say that y equal to 1 is the horizontal asymptote. For this graph, when x is approaching infinity, you see that the graph value approaches y equal to negative 2. You see an horizontal asymptote at negative 2. Similarly, when x is approaching negative infinity, you see a horizontal asymptote at y equal to 4. In the next example, in the first figure, y equal to 1 was a horizontal asymptote, whereas in the second figure, we had two horizontal asymptotes. We did discuss this in the graph. So there's a note here. To find the vertical asymptote, you always start with the denominator. Equate the denominator of the rational function to 0 and you're going to solve it. For the horizontal asymptotes, the horizontal lines that the graph of the function approaches as x approaches plus or minus infinity. So in this example, you're asked to calculate horizontal and the vertical asymptotes. So let's do this. Let's calculate the vertical asymptote. So we are asked to calculate the horizontal asymptotes here as well as the vertical asymptotes. So let's do the vertical asymptote calculation. We start with the denominator. We're going to equate this to 0. So this is x plus 2 times x minus 1 equal to 0. So we have x equal to negative 2 and 1 when we solve. So we say that the vertical asymptotes is x equal to negative 2 and x equal to 1. Now the calculations for the horizontal asymptote. We discussed the limit value x approaching infinity 2x square positive x negative 1 divided by x square positive x negative 2. You see that both the numerator and the denominator are the polynomials. You also carefully read the degree of the polynomials. They are the same, they are equal to. Degree in the numerator and the denominator are the same. So when you have this particular case, when the degrees are the same, you're good to write the coefficient, which is 2 in the numerator, the coefficient of x squared, which is 1 in the denominator, and your answer is 2. You can do this trick only if the degree in the numerator and the degree in the denominator are the same. If they are not the same, we cannot do this. So let's learn a method to solve the limit value. Limit x approaching infinity. You have 2x squared positive x negative 1. You have x squared positive x negative 2. You want to divide by x squared, the highest degree in the numerator and the denominator. So you have limit x approaching infinity, 2 plus 1 over x minus 1 over x squared. And then you have 1 plus 1 over x minus 2 over x squared. So when you do this, when x approaches infinity, you understand that each of these limits are going to be 0 when x approaches infinity. So you say that this is 2 over 1 and your answer is still 2, which is same as the method by comparing the degree. In the next example, you're asked to calculate the limit when x is approaching infinity. When x is approaching infinity, it's always the horizontal asymptotes. And you see the degree in the numerator is 3, degree in the denominator is 3. So you're good to write the coefficient in the denominator is 1. The coefficient in the denominator is 2 for the highest degree, and the answer is 1/2. In the next example, you are asked to calculate the limit when x is approaching infinity. So when you have x approaching infinity, in the first step you plug in infinity and check the value. It's infinity when you simplify. Well, when you write infinity, you don't say the limit is infinite, whereas these are the limits. When you have infinity minus infinity, the format is called as indeterminate form. So you still want to do some algebraic method to calculate the limit. So for this, you want to start by dividing the numerator and the denominator by 1 over x. So let's do it. So this is one method. Divide numerator and denominator by 1 over x. So the new fraction becomes x approaching infinity. You have, I'm sorry, it's not dividing right away, but you see a rational function, a square root a minus b format. A square root a minus a square root b or some other term. When you have such rational terms with the irrational square roots, you might always want to do the rationalizing technique, which we learned in one of the limit sections. So let's start by rationalizing this function. So this is limit x approaching infinity. You have square root 9x squared plus x negative 3x. So multiply a similar term with a different sign. 9x squared plus x positive 3x divided by square root 9x squared plus x, and then you have a positive 3x. Now in the numerator you have the format a minus b times a plus b. It's similar terms. So this will give you the product, which is the difference of square a square minus b square. So let's do square of the square root. So it's square root 9x squared plus x. You have a square, and then you have 3x squared. So I'm going to write 3x and then a square for this. Divided by the denominator term 9x squared plus x plus 3x. The limit x approaches infinity. We know that square of a square root is just the term. So let's simplify this. This is 9x squared plus x. And let's square the second term. Square of 3x is 9x squared with the negative sign. So you see 9x squared cancel because when you subtract it's 0. Divided by 9x squared plus x plus 3x. Now at this step, you're seeing x in the numerator and you have 9x squared plus x plus 3x in the denominator. If you plug in infinity in the numerator and the denominator, you still see infinity over infinity form, which is an indeterminate form. So at this step, you might want to divide the numerator and the denominator by 1 over x. So the fraction in the numerator becomes just 1, and in the fraction in the denominator becomes, when you divide a square root term by 1 over x, when the 1 over x goes inside, it goes inside as a square function. So it's x squared, and then it's x over x squared. Whereas the last term here, you don't have a square root, it's just 3x. So 3x can be written as 3x divided by x. So let me write the next step here on the top. So you have, simplify this x square after dividing x and 1 over x square, and you have x and x getting cancelled. So when you do all this and you see that you have just one term with 1 over x, and 1 over x when x approaches infinity is 0. So this becomes 1 over square root 9 plus 1 over infinity plus 3. 1 over infinity term is 0. So you're going to write this as 1 over square root 9 is 3. So 3 plus 3, so it's 1 over 6. You can understand the square root is only for 9 and it's not for 3. So we'll end this section here.